Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello and welcome to the webinar series with academics of the IT Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open our webinar today with Professor Enrico Natalizio from Technology Innovation Institute, UAE, and Université de Lorraine, France. We count on your support to make this webinar an interesting experience. So please submit your questions via the Q&A channel. We will address them to our speaker during the Q&A session. And after the Q&A session, as just announced by our avatar, I will moderate the Wisdom Corner, live lessons. So please stay online. Professor Natalizio agreed to a personal chat. He will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm pleased now to introduce Professor Ian Akilditz, Editor-in-Chief of the ITU Journal and founder and president of Truva from the United States. Professor Akilditz is Ken Byers Chair Professor in Telecommunications Emeritus at the Georgia Institute of Technology. Professor Akilditz has established many research centers worldwide, including in South Africa, in Spain, Saudi Arabia, and Finland. He is Editor-in-Chief Emeritus of Impact Factor journals and highly cited and at the top of the most prestigious international rankings, visiting distinguished professors in many universities around the world. His current research interests include 6G wireless systems, terahertz communication, metaverse, and communication in challenged environments. So, Professor Akilditz, the floor is yours for your opening remarks to introduce our speaker and then moderate the Q&A session. Thank you.
Thanks a lot, Alessia. Good morning, good afternoon, good evening, good night from Atlanta to all around the world. I again welcome you all to our ITU Journal Future and Evolving Technologies webinar series. This is the last webinar this season. We started this webinar series back in 2022. We had some of the best researchers, including academic and industry leaders, talking on very popular and diverse topics in our series. Please go to our journal's website and watch the previous webinars. They're also available on YouTube. Your feedback and suggestions will always greatly be appreciated. We have another excellent researcher and speaker today, Professor Enrico Natalizio from Technology Innovation Institute in Abu Dhabi and University of Lorraine in France. Before I present Enrico, I would like to briefly talk about our journal. The objective of our journal is to bring the academic and industrial worlds together in order to establish a strong bridge between academia and industry. The idea for our journal was initiated back in December 2019, and our first issue was published in December 2020. It is an open access journal, no fees for readers, no fees for authors. The papers go through a rigorous review process, and we try to cover all forefront and timely research activities in the academic industrial world. The journal is a product of a big team effort, and I would like to acknowledge them here. Cesar Onosan, Bilal Jamusi, Alessia Magliarditi, Erika Campilongo, both Marias, and many others for their work, efforts, continued support, and dedication for the success of our journal. I encourage you all to submit your papers, and also if you have ideas for special issues on popular topics, please do not hesitate to contact us. Today I have the great pleasure to present you our speaker, Professor Enrico Natalizio. First of all, on behalf of our entire journal team, I personally thank Enrico for accepting our invitation and giving this webinar today. Enrico Natalizio is currently Chief Researcher of the Autonomous Robotics Research Center with the Technology Innovation Institute in Abu Dhabi and a full professor with Laurier Laboratory at the Université de Lorraine in France. He obtained his master's degree with magna cum laude and PhD in computer engineering at the University of Calabria in Cosenza in Italy in 2000 and 2005 respectively. In 2005 and 6, he was a visiting researcher at the Broadband Wireless Networking Lab. It was my lab, actually, at Georgia Tech in Atlanta. And from 2006 until 2010, he was a research fellow at the Titan Lab at the Université de la Calabria. In October 2010, he joined POP's team at ENRIA Lille, North Europe, France, as a postdoc researcher, and from 2012 until 2018, he was an associate professor at Université de Technologie de Compiègne and full professor at the Université de Lorraine from September 2018 on. He has been editor and a member of editorial boards and special guest editor of several leading journals in network and communications, as well as serving on the steering committees of many IEEE and ACM and other organization conferences. Over the years, he served in various capacities in the organizing and technical program committees of the number of conferences. Based on Google Scholar, his H index is 33, and total number of citations to his paper is almost 6,000. I almost mentioned dollars, 6,000 citations. He has been ranked in the top 2% worldwide scientists of the Stanford University's bibliometric study for the year 2021. Enrico contributed many pioneering papers on the topics of network communication protocols, in particular on drones communication networks, the last 2 decades. His contributions on UAVs and drones are very highly recognized. In recent years, he obtained many excellent results regarding drones communications and underwater networks. He continues to produce high-class, practical, and impactful papers. His research interests include UAV communications and networking, robot and sensor communications with applications in networking technologies for disaster management, infrastructure monitoring, and IoT privacy and security. On a personal note, Enrico and I go back almost 20 years. I met him in Lipari. This was a summer school back in 2004. He was still a PhD student at the University of Calabria in Cosenza at that time. He had many other friends, and we had great time in Lipare. I had liked him right away as we shared many interests. I don't want to go through those interests here. The people who know him and me, they know what I'm talking about. I had invited him to join my research lab, broadband wireless networking lab at Georgia Tech. And he came not only one time, but many times afterwards. There were many, many other reasons, by the way, not only research. He loved USA and Atlanta, and of course me, right? And I visited him in RIA, in Lille, University of Compiègne, and University of Lorraine, and now at TII. He created and leads this very large group at TII from the scratch the last 4 years. I witnessed that. So my hat is off to him for this great success. He gathered almost 30 plus people, top-notch people from all around the world. They are conducting research in robotics, drones, and their communications. I have been working with Enrico since many years, and we published some good papers with high citations together, and also received a couple patents recently together. It is always a great fun to spend time with Enrico personally and on the professional level. Enrico is one of the nicest and honest, reliable, and great persons I met in my career. Again, thanks, Enrico, for accepting our invitation. We welcome you to our webinar series.
Thank you, Professor. Thank you for the introduction. Thank you for the invitation. Thank you also, Alessia, Maria, and the other people involved in the organization of this webinar. It's really a pleasure for me to speak for the ITU journal today. So I will share my screen. I think you can see my screen, right? So my talk today is on networked robotics and the communication system, the interface between the two, the crossover among different disciplines that form these new disciplines of networked robotics. First of all, I want to acknowledge the work of 3 of the people in my team that helped immensely to put together this presentation, like preparing videos and getting images, helping with the brainstorming and so on. So what the presentation of today is about, I will just move to the next slide. Okay, here. The table of content of the presentation today is about networked robotics. So we have to first of all focus on what a networked robotic means, and what is the main component of a networked robotic system. That we will focus on the multi-robot autonomous system part, just to give the most difficult, I would say, and the most challenging environment to understand some of the most important concepts. Then it will be split just in 2 main parts: what communication can do for robotics and what robotics can do for communication. And then we will get to the conclusion. Basically, this research started actually when I started visiting, the first time that I visited Professor Akildits at Georgia Tech, because at the time I was working on, it was 2004, 2005, I was working for my PhD on handover mechanisms for a cellular system. And when I say cellular system, at the time it was GSM, that means second generation. So there was this problem of having cars or people moving with their telephones and having to be handled between 2 different tower cell of a cellular system, and how the system should cope in order to face the problem of the fact that they were moving, and so the signal will go down for one cell and maybe up for another one, and so the communication should be switched to the other cell. This became, after some work on this in this field, it became actually, let's say, I had a flip of the perspective on the moment I visited Professor Agilditz in Atlanta, because I started thinking why mobility should just be a problem in a communication system. We might use mobility for improving the communication as well, which was something that naturally, actually, we still do when with our phone, we don't have signal in a specific place, we move away and we get more signal somewhere else. We are basically using controlled mobility in order to get better signal. But it was not a concept that in the community, in the communication community, or in the robotic community was really understood or was really used in a scientific way. The thing that usually was done from the roboticists was to assume for their system of robots just perfect communication, perfect models of communication, and perfect interfaces. And this, of course, was the main cause and still is in many cases of the failure of the robotic system in the end. On the other side, communication was clearly useful for robotics, but has never been pushed towards robot, and still there are many challenges and many steps to achieve in order to have a complete communication suite for robotics. So here I want to start just to introduce the talk. I want to start with this video that we have done at TII. Professor Akildis mentioned that I'm leading now this big robotic research center of 250 people, aiming at 300 in a couple of years. And in this research center is organized around different teams, different disciplines. We have the control and decision making, the swarm and coordination team, the perception and vision team, and then we have a communication team. And this was actually one of the first, I think, in the world that decided for our center, we decided to have a communication team included into a robotic research center. Usually, as I said, communication, there might be one expert of just the communication technologies needed within a robotics center, but not a whole department with people just doing research for that. And I want to introduce the concept, especially of multi-robot. That is what I will speak about by giving you an example of one of our realization that was made for a search and rescue scenario. So we have the idea that something happened in a specific area, and we have this helicopter that represents. We haven't done the helicopter; it's just a partner that provided us with it. But what we have done, as you have seen our collaborators, we mounted these 6 drones below the helicopter that represents the mothership that gives the backhaul communication towards the ground station. And the 6 drones are dropped from the sky, and they go searching for potential people in distress. We have here desert or water, so you will see in the first image you saw them spreading over the desert and looking around, and now they go on the mission outside in the sea. So what they move information, and then they are supposed to find, in this case, a boat that's simulated by this big QR code that we have put on this floating device, and transmit the coordinates of this boat in distress with people probably having injuries or having problem on top to the operator. The operator decides to send a boat. As you see, these are all unmanned vehicles. There is no pilot, and the only role of the operator here is to send information on where to go. That's it. Then you see that the bot is able to avoid obstacles that we had put on the path, on the straight path, and get back to the main path that was decided. And then it drops these smaller robots that have the role to go and bring first aid, supplies, water, medicine, whatever might be needed towards the people in distress in this boat. We have done this for, as I said, for the marine environment, but also for the desertic environment. And you will see at the end of this video that these smaller drones are also equipped with camera, and they send back the video streaming of what they see in the target zone. So I wanted to introduce with this video because here you have a clear idea of a multi-robot system. In this case, is a 2 segment of those on which we work are involved, the aerial and the marine. We have done, as I said, also with aerial and terrestrial, and we imagine to have a complete mission with the 3 segment aerial, terrestrial, and marine all involved. This also helps me giving the introduction towards the autonomy itself. So multi-robot is clear, is just a fleet of robots that do things together, but which is the level of autonomy that they can reach? This is something that is, let's say, standardized. Allow me this term, even if this is just a common general agreement on the level of autonomy that these devices may have. So this scale of levels goes from 0, where there is no autonomy at all. I will not go into the details of all the things that you see in this slide, but just for you to have an idea, level 0 is the operator in the loop that basically does all the needed, gives all the needed information, is able to pilot the drone, and without the pilot, the drone will not fly. So here I'm talking of drones, but we can extend these concepts to any other kind of robot, marine or terrestrial. So level 0 is no autonomy at all, and the level 5 is complete autonomy. Complete autonomy means that the operator just has to set the objectives, and then the system is able to fly or to move under any condition, has full understanding of what's happening around, and can fly through any environment. In the middle, of course, there are many other levels. So level 1 to level 1 and level 2 are still levels in which the autonomy is partial, and the pilot is needed to fly the system. From level 3 on, and especially in level 4, A, B, and C, the operator is not flying the system anymore. The drones are able to fly by themselves, and they are able to do progressive incremental operation that allow them more and more autonomy towards the full autonomy of level 5. I needed to introduce this because you see, and you also understood probably from the video, that communication plays a big role inside the multi-robot system. Is not simply model. It's not okay to simply modeling it as a perfect communication, because there are so many issues on one side and so many support that communication can actually give to a multi-robot system. Here, I wanted to describe 4 of the main element or features, I don't know how we want to call, but they can be even research areas of what communication enables for autonomous system. So the first of all, the first of the 4 is the link layer communication. That the main basic work that we want to do with the communication is to establish a connectivity between the different robots or between the robot and the ground station. This is the first and the most important, I would say, in order to create the communication frame to allow the connectivity among the different drones. This is drones or robots. I'm using it interchangeably, but you can think of robots in general. So in these and the following slides, you will always see this what is for. That is the role of this element of this research area within a multi-robot system. How this is studied. So what is the methodology that in general is applied to determine schemes and algorithms and solutions that might be then practical, and then which are the challenges that are still important. Furthermore, you will see this ISO-OSI stack on the in the middle of the slide that represents where this area of research focuses if we project it into the classic ISO-OSI stack representation of communication. So as I said, the link layer communication is there for established connectivity, and considering that we are talking of communication that sometimes don't need to go up to the network or the transport layer, because we just need connectivity and sending information that usually might be either control information or just data. What we need is just to stay at the physical, at the data link layer. At this layer, still we can do quality of service management. We can do data framing, error detection, and all the things that we know of level 1 and 2 in the normal scheme of communication. Now, how this is studied specifically for this kind of networks made of robots that communicate with each other and potentially also base station or any other infrastructure. It's kind of the methodology are kind of similar for this slide and the following that you will see. The usual theoretical analysis with mathematical modeling, so develop models that describe the behavior of the protocols or the channel below, and then use queuing theory, probability theory, and so on. Then in the theoretical analysis, a big part is also given by the performance analysis that is very relevant in this case. And the key performance metrics here are the throughput, the spectral efficiency, latency, jitter, packet loss, and so on. In the simulation part, so the second item of how the link layer communication are studied in multi-robot system, we have the possibility to, or with the different kind of simulator, to have a 3D environment completely reconstructed and having virtual flights or virtual movement of terrestrial robots by using GIS data. Then in the simulation part, we have also the radio propagation that is relevant, how this is simulating. We have ray tracing now that is used more and more for modeling the channel conditions. And there are various electromagnetic simulator like ANSYS that also can simulate effects of antenna and also the effect of, for example, the frame of the UAV, the drone, or the car, if we are talking of terrestrial robots. In some cases, also mobility is simulated. So, for example, in MATLAB, there is a UAV package that also takes into consideration the mobility of the UAV. Next methodology is emulation. So in this case, we have tools that allow the emulation of the network like Mininet and Emulab that are used also in multi-robot networks. And the one thing that is done for the emulation part is to put the hardware in the loop. So combining the real hardware with the emulated components that allow to understand what would happen in realistic condition. Finally, and I would say in our case at TAI, we are much more pushed on the experimental part. There is the testbed, the classic testbed that use operating system like ROS, for example, that allow to operating at higher layers. It allows also to connect to facilitate link layer communication or understand what will happen with or without link layer communication. There are even smaller version of ROS because one of the main problem of the robot operating system is the size and the weight, which are more tailored for microcontrollers. So there are micro version of ROS. And then the other thing is creating a testbed based on software-defined radio. In this case, we can push the communication part much more, and this integrated in a good platform of robots, it can give direct results and direct solution. Now, if we look at the challenges of link layer communication within the multi-robot autonomous system, what we have is that, first of all, we have to consider that we will be in an environment that might change because this might change in time because the robot moves, but also, as you have seen in the video initially, we have different kind of environment. There is the marine environment with the water and the surface of the sea, as well as the sky, and so the potential line of sight, the constant line of sight with something up in the sky. So adapting to the environment and finding solution that can adapt to the environment is one of the main challenges. The other one is that we are connecting different networks in the end, especially if we work inter-segment, and the interoperability of this different segment, considering the different channel, line of sight, no line of sight, system that interfere with each other. We have UAVs, and in the example of the video, we had boats that are communicating at the same time, and so on. Or, these are all problems that need to be solved for a full-fledged solution. Then we can have, in some cases, when we don't have such big devices like small drones or nano drones, we have also to cope with the fact that they are resource constraints. And so we have limited energy, limited communication, computation capability, and so on. finally, one of the problems that we are trying to face recently also in our team is what if we want to have 100 or 1,000 robots communicating all at the same time and work together to do a mission. So not only being in the same environment, but also being able to do something together. This is the last problem of scalability in the bottom. Then next area of research or feature that are communication enablers is the sensing. So sensing, I guess, is something that all of us have it clear what it means. But I just want to give a small example based on another one of the big projects that we had recently. That is the AI car that we have, these TIA racing cars. You see that is unmanned. There is no pilot in the middle. What we have done recently in Abu Dhabi is to make it compete against a human car, the same car, but driven by Formula One pilot. And put them together in the track in front of 10,000 people in the audience and see who will perform better. Of course, the human car is still superior. So this is the pilot of the car. So it was 10 seconds, sorry, out of 2 minutes of lap time that was better. But still, I mean, there is a improvement to do. Why I wanted to mention this in the sensing part is because the car that you have seen, in order to make it unmanned, so remove the pilot and let it just run into the track by itself, it had on board, it was equipped with 3 radar, 4 LiDAR, 7 cameras, and other devices, other sensors in the tires and in the frame and so on. All this because it was super important to have the possibility to make decision at the milliseconds level or even more faster than that. So all the sensing part, you understand that is a lot of data that needs to be collected just for this application specifically, and that needs to be treated and understood. If we move the perspective, looking instead of aerial robots, so UAV, we see that even the constraints and the capabilities are different. If we think of simply of a sensing based on UAV that can normally flies not so high, up to 1,000 meters, we have a certain coverage, a certain capability of detecting things, accuracy, and so on. This, of course, changes if we go on bigger airplane or even on satellite. So the sensing part, collecting data, understanding the scene, and putting things together. This is what sensing is for. Requires a good let's say understanding of how to study and how to put things together in order to be an enablers for the communication and allow communication to support multi-robot system. How we studied again is similar to what I said before: mathematical modeling, simulation. In this case, for the simulation, we have specialized simulators like Gazebo or VREP or WebBots that are able to simulate sensors in virtual environment. So this gives a perfect idea of what happens if I put a LiDAR or a camera or an ultrasonic sensor on a robot, and just by the simulation part. But in this case, I wanted to add also the machine learning part, which is very relevant, because in this case, for the sensing, we have the need and the possibility to train models, do deep learning, reinforcement learning, and so on. And being able to detect and to have eyes and ears for our robots that understand the scene according to what they have already seen and the model they have been trained on. And then again, the experimental testbed is the closest to reality. Now, if we look at the challenges in this case, and I have put the sensing only on the physical layer, because in the end they detect and measure physical world, and this for the communication part, it also goes on considering devices that have certain capabilities related to the distance, to the frequency, and so on. The challenge is how I put all those data that I collect together in order to make decision with a certain speed and in an effective way. So all the data that you have seen, for example, in the car video, that has to be fused somehow, and whatever the camera we're seeing, the LiDAR we're seeing, and the radar we're seeing needs to be put together, and how to make an effective sensor fusion is still something that is very relevant for this area of research. Then we have the usual problem of having noise and uncertainty in the measurements that the sensors have, how to avoid systematic error in that, or how to avoid even sporadic error and make the measurement still effective for the application that they are running on top. Finally, according to the platform that we are considering, again, if we have limited resources, for example, thinking of having onboard processing of the data might be prohibitive. So the only thing in this case is to transmit or let it go towards a central server somewhere that can do the processing. But doing it on board, of course, brings a lot of advantage. And so how to do this effectively is still one of the main issue in this area. Next topic or research area for multi-robot system is distributed computation. So distributed computation means to make a task and to have a certain number of devices that are able somehow to cope with this task together. In order to do this, they need to decentralize control and make a decision in a distributed way. They have to schedule each other task each other part of the task in order to perform finally the task together, and offers some resistance, some robustness to the system itself, and tolerance in case any of the robots that is in the system is defective. How this is studied, and in this case I put it the application layer, because here the distributed computation for us means having a task and being able to perform it. So for the communication part, this is something that is done on the application layer. And how this is studying, again, we have the mathematical modeling for the theoretical part. Optimization plays a big role because we need precise scheduling of events that will happen and the task that will be performed in order to complete the mission altogether. And so, I mean, optimization is mentioned there. We have the need this time also to make decision, and to make decision in a way that the robot agrees with each other. So here, one of the most studied thing in this field is how to define a good consensus algorithm. But we also need to analyze the system and understand the real-time outcome of what we are seeing, and understand if this matches with the expectation that the solution was supposed to have. So here also tools for real-time system analysis are really relevant. Which are the challenges in this case is how to decide which is the best model for distributed computation that is effective for the kind of task that is requested in a certain time, in a certain situation, how to manage the data that comes from the different drone in order to have consensus algorithms, for example, that might be effective for what they need to do, how to coordinate if the task is actually pretty complex, if I don't have just to do my part and go ahead with my life, but instead I have to wait for each other feedback in order to go ahead in what I'm doing, and also how to validate an algorithm in this case, unless I have the real life that shows if that works or not, but how to understand all the corner cases still remains a problem. Last, for this part of the presentation is last topic or last research area is the coordination and cooperation. This is one step ahead in respect of the distributed computation that we have seen before, because distributed computation somehow was once the task is split and given to the different robots what is important to do. Here instead is even how to allocate the task and even how to manage tasks. So if I have just a complex mission, how can I split these in different submissions, tasks, and so on, and how to share these on robots that might be even in different segments. So in aerial part, but also in terrestrial, marine, and so on. Furthermore, how they would share the information with each other, and how they will do in this case a decision making that might be collective with different measurements, different environment of sensing, and so on. Again, the methodology for this case is the usual one: theoretical analysis to understand if with the probability theory, with the queuing theory, and so on, if the network is actually working well for the purpose of the coordination and cooperation that is needed. But then also simulation, emulation, and of course testbed. So this is, as I said at the beginning, the classic operation that the classic methodologies that we use to validate a scheme of cooperation and coordination among robots, and that are supported by a communication layer below. Here I put application and physical layer as the most relevant for in the ISO stack for coordination and cooperation, because this not only can be good at the application layer, which I think is intuitive for everyone. Once I give a mission to a multi-robot system, and this is split in task and in a subtask and so on, of course, I'm working in the ISO stack at the application layer, but actually it can somehow be beneficial or being supported also at the physical layer, this cooperation and coordination. And we have an example that we will see again later, more extensively in this picture in the bottom right of this fleet of drones used as a MIMO antenna, as a multi-MIMO antenna, that cooperative MIMO antenna that transmits something to some remote users, increasing, of course, the capacity of the channel towards them by communicating in the same time. So this is something that, of course, is done at the physical layer, and so I wanted to mention here in the cooperation part. Now, challenges in this case, of course, is how to limit the exchange of control and let's say coordination, communication among the different robots in order to arrive to a full autonomy without overwhelming the underlying network with data that might be irrelevant. Also, how to allow all the fleet to work together and to make actions that at a certain point needs to be synchronized. And also, again, as I mentioned before, how to allow the performance of complex operations. So this part, this slide concludes the first part, and now we will move to what communication does for robotics, and then we'll see the other way around, what robotics does for communication. So communication for robotics, this is second part, will be quicker on it. It's which are the technologies and architecture for multi-robot autonomous system that base their cooperation, coordination on the underlying communication. Which are the application and which is the current regulation and standards for communication for robotics. So first of all, the architectures. Classic on the left, we have one ground station that communicates one-to-one with different UAV. You can imagine again that these are boats, autonomous boats or autonomous terrestrial vehicle, as you prefer. We have a second scheme here that is decentralized, so with more than one robots at the same time and not having a center of the star that detects or receives all the communication, but also allows some possibility to communicate with each other. This is a classic centralized, decentralized architecture that was the same also for any kind of wireless network. We have two more that are interesting. Is interesting to mention here. The first one is this vertical towards the space, through the different atmospheric layers, communication of different kind of aerial robot in this case, so satellite or high altitude platforms or drones that at different level they can somehow communicate with each other and support each other communication and application if there is anything running on. And on the right, you have a more specific example that is now well represented in the non-terrestrial networks, where we have ground networks, aerial networks, and space networks. So these within the same ecosystem that exchange information and make a non-terrestrial network able to make a user of a non-terrestrial network able to communicate with the system or with other users and run its own application. So these are architectures that are coming up more and more, and that consider robots as part of the communication architecture itself. And you see that basically this supports the behavior of and the application that we want to run on. If we go specifically on the technologies that are needed for multi-robot autonomous system, we have a different way of making them exchange information, collaborate, and achieve a higher order goal. We have some that comes from nature, like bio-inspired pheromones, for example, for implicit communication. But those that are listed in the last item of this list are actually the technologies that we are currently using in order to make robot-to-robot communicate with each other. We will see them quickly, each of them in the next slide. But first of all, I wanted to show the progress of the communication technologies since 1997 or even before, where we started with underwater robots and with acoustic local area networks with different kind of modulations. And this went ahead, and you see that in the different years and the different the different member of the family of IEEE 802.11 or .15, some incremental usage and some incremental, let's say, research on the increasing the capacity of the network or increasing the being able to handle the speed of the device that are in the autonomous robot system, or extending the range and being able to reach farther or according to the application, smaller distances. So this you see that going ahead in the different years, we are moving towards capabilities that allow networks of robots to communicate on a large scale with low latency, with the resilience for potential failure or problem, and that allow large deployment of swarm. Now, going back to the technologies that we are using currently, first of all, as I mentioned before, there was a big step with the B2B, with the vehicular technologies that started considering the 802.11p group of standards that somehow were those that introduced mobile devices moving with a certain velocity that is not negligible, and that is still able to keep up with the communication. So this is one of the family that I wanted to highlight here, because this was a big step. If we go back, it was around 2010 or before, when 802.11 NMP were introduced in the 802.11 family. The second one is the personal area networks, as they were called some years ago. So the 802.15 family that allows the usage for a short distances of very effective protocols for communicating. These were used originally in wireless sensor networks, and then they moved to multi-robot system as well. Same concept, but extending the range of communication is the one given by LoRaWAN, that is based on 802.11.15.4, sorry, and extend to several kilometers the mission range. Now, next generation in this sense is the Wi-Fi 802.11ah that uses sub-gigahertz radius, and this has already been tested and used in factory automation successfully. If we move to the second group of technologies, is the cellular networks. So here we are exploring which are the technologies that allow communication in multi-robot system. First of all is clearly the family of 802.11 or 15 that are good for the classic Wi-Fi. So the wireless local area networks, but of course even cellular networks are used to have robots considered as a terminal or user equipment, if you want, of a cellular system. In this case, we already have technologies related to MIMO, beamforming, and the cellular to vehicle to everything. You have the image on the right that represents a vehicle communicating either with an infrastructure or among themselves, or even with a drone. and even with satellite. In this case, specifically, these pictures also show one of the next generation technologies that are the reflective intelligent surface that allow to extend and to cover bigger areas in the communication by these surface that are put in strategic places that allow this reflection and extension of the signal. Other technologies that are considered as next generation, but some of them are already used in multi-robot system, is the side link for UAV, for example. So in this case, you have in this picture the base station communicating with the single robots, and this extending the coverage of the cellular station, the cellular base station, through the side link that basically with the same standard, the same protocol keeps communicating outside the range covered by the base station. Then we have a more futuristic kind of communication that might be useful for a multi-robot system that are holographic MIMO or even metaverse. Next is a group of technologies used for multi-robot system is a proprietary and tactical radios. So in this case, we have this brand mentioned, DTC, the Lab Silvus. These are brands of proprietary radios that allow communication among robots. These are the easiest for us to mount our testbed because basically they already come to survive in extreme environmental conditions, have a very low latency. They allow mesh operations, so we can create mesh networks in the sky. They have their own waveform that allows encryption in built-in way, and they can transmit and receive in beamforming ways. So it's they are let's say the most versatile for quick testing of potential algorithms or a scheme of coordination, cooperation, and in the end, performing mission in multi-robot system. The last one that is not to consider a technology, but I put it here anyway because it was useful to have it represented, is the non-terrestrial network that I already mentioned in the architecture part, because it's not only the architectural part, but also the technology that is needed in order either to connect different atmospheric layers, so this is standardized and allow communication between different atmospheric layers, or even within the same, let's say, layer, have communication among different parts that are represented by the ground network, the aerial network, and in case we go to the space, even the space network, in order to have a user somewhere on the ground or in the sky that is always connected. This moves also to non-terrestrial network, also to the concept of interplanetary interconnection, or even creation of the network on planets that have no other kind of coverage, of course, otherwise. Now, application for that requires communication to allow robots to do things together. You can imagine as many as you want, and I think here the list could go ahead with all the different sector of domain of application. Those that are more represented in literature, but as well as in real life testbed and application, are related to disaster relief. We see drones flying after a big flooding or after an earthquake in order to assess what's happening around the territory, how it changed, and so on. In agriculture, in industry, in healthcare, in transportation. Here on the right, you have this image taken from a recent paper that shows a multi-robot system working for us: assembly, transportation, manipulation, painting, formation, 3D printing, and so on. So the kind of task that they can do together are clearly very varied, and they cover many of the sectors of interest that one might have. Now, looking at the standards for communication for robotics, there have been efforts. In this picture on the right, sorry, we have it's the situation until 2020. This is from a paper that we published in 2021. But you can see that 3 of the biggest consortium of telecommunication, including ITU, are thinking of including UAV because it's clearly the most evident, let's say, benefit that a network will get, or a mission will get in having robots that fly. included into the communication network itself. So this is something that has been done by EEE with a specific work group, by 3GPP in the different release that included more and more standardization and support UAV or UAS connectivity, identification and tracking, and so on. However, the situation is still that there are no standardized protocol for robot communication. There is a lot of the candidates in terms of technology. I mentioned three, let's say four of them with the non-terrestrial network, but not one that is considered as the one that is the most important or the most prevalent. There are no standard message that are exchanged among robots. There are tentative in this sense, but still this is very dependent on the vendor and on the robot. So there is still much to do in this sense. In this slide, I also put what will happen after 2020. And so here you see that through the non-terrestrial network standardization, probably some support will be given for sure to the consideration that the infrastructure itself might be composed with robots, and this will come in the next group of slides that you will see, but that robots might become users of a communication system, and in this case we need to support the end-to-end component that you see, especially for 6G, but also for the 5G part, and so on. Just to conclude this part with the regulation, how now drones or other kind of robot are regulated. Here you have just the summary of the regulation for drones across different countries. So you see that according to the country, on top you have China, US, European Union, UAE, Singapore, and Australia. That there are different rules on what you can do. So the application that you can fly a drone for, if it needs registration, if it needs to be cleared from the security of the country, if there are rules on determining where it can fly, which is the age at which you can fly different kinds of drones, if there are restrictions to fly nearby airports or nearby residential areas, and also which are the paths that the flight can take. So you see that it's very varied, and especially in this last one, the flight paths, having a visual line of sight or not having visual line of sight is a big hindrance for the development of multi-robot systems that are completely autonomous. Now, if I move to the last part of the presentation, it's much shorter because this is more research oriented, I would say, and is what robots can do for communication. Till now, we have considered communication, how it can support robots doing submission. So, for example, having drones flying because they have to monitor an area and they need to be connected. So communication supports the connectivity of these drones in their performing their missions. But which are the other way around? How we can use robots to augment the infrastructure of a communication, for example, or augment communication that are needed ad hoc on certain area. And this is, let's say, more the part that we are pushing in a different environment. So just as an example for you to understand what we're talking about, we can imagine sensors deployed on the sea, on the bottom of the sea, and transmitting their information towards an infrastructure. In this case, we imagine that the infrastructure is represented by the surface buoy, and these data are communicating outside to the main infrastructure that is in the land. So in this case, these buoy can be robots that actually collect information and share the task of defining where to go, what to do, and how to move on the surface of the sea in order to collect all the information that comes from the sensors below. But this is also something that has been tried in the last probably 20 years by using even more, by using low altitude platforms and high altitude platforms to offer coverage to a large area. So in this case, you see that we are basically using the robot to create an area of coverage for the signal of communication to the user, to the end users. And there are examples, recent examples, where these are used for data transmission, for navigation, for computation, caching, and so on, different kinds of services that are offered by high altitude platform. So high altitude platform has never been considered like as a robot, but basically this is what it is. It can be completely autonomous. We can have different level of autonomy, or it can be completely controlled by a human pilot. But still is a device that will be in the sky to improve the communication of an area. And then the most evident example is the usage of drone in cellular systems. So in this case, drones that are deployed in an area where there is no more or there was not at all from the beginning communication coverage. So for example, in this case, we are talking of disaster or public emergency. The communication goes down because the cellular network, the infrastructure drops somehow, collapses. And we need on-demand connectivity. It might be used also to extend the connectivity and the coverage of a base station towards the users that is outside the area of coverage of the current cellular system, or it can be used ad hoc to improve or increase the capacity of an existing infrastructure. So in this case, we have put the example of the Expo 2020, where 1 million people were gathering more or less in the same area, and clearly the network will not be able to cope by itself. So redundant base station, but as well as the UAV, can be used to increase the capacity in this case. This is for the infrastructure part, but also when we don't have infrastructure, we can imagine that a network of robots could support communication and could create connectivity. So here we have an example taken from a survey that is based on this communication system creating ad hoc to monitor specific situation, for example, in mountains where there is no connectivity at all, and we still want to control what's happening around without even having a communication system. Here, there is the ground control station that has to be considered as a control station for the system, but not a cellular system. So in this case, again, we have the possibility to use a robot to improve communication, to relay information, to create coverage, and to create connectivity on demand. And here you have the complete picture of the image that I showed before. That was the one on the top right, where the fleet of drones were used as a virtual antenna array to increase the capacity towards the remote users. The same fleet of drones could actually be used to overcome the power of a potential eavesdropper in an area where this might be needed, or they might be used to overcome the interference towards a specific base station, or they can even be used in the integrated sensing and communication to get information and have the possibility to increase the accuracy of the measurement. So these are all examples of how robots would improve the communication part. And we have some examples that I want to show you that we have worked on. So just a couple of videos on what we have done here at TII in this sense. So the first thing was that actually we have mounted a 5G base station on a drone, and we have tested some relevant algorithms for mobility. So here you have the schematics of what it's on top of the drone, and you see here that we have a flight controller that is so here we are considering autonomous drones, so not remote controlled, of course. And you see that on the offboard PC that supports the operation of the flight controller as well, and does the communication and supports the usage of a service of communication towards some users. We have this middleware that is represented here, and this middleware is something that I would show, if I can, in the immediate following here. Is composed by 3 main controllers that are the app controller on one side, just to check that from the application point of view, everything is going in the right way. But we have drone controller and net controller. So in this case, we are taking into account and exchanging information between these 2 controllers, that one represents the communication side and the other represents the control of the drone itself. So this is probably one of the closest example to that, which was the meat or the main objective in including the communication in including the mobility, in the communication stack somehow, and allow through the mobility to control the network and vice versa. So the effect of this is here you have an example of picture of the drone with the 5G base station mounted on top. And here you have one application that is possible now that the network and the controller of the drone are intertwined somehow. Imagine to have an area where you have different terminal users of a 5G system, for example. Where should the drone go in order to serve all of them in the best way possible? Here we have what our schemes do. You see the guy on the bottom using his cell phone and being connected to internet, and the drone initially staying here. But when, or maybe moving away and then activating a flow of data, and then the drone automatically reposition itself in order to offer the best coverage to the person that is on the ground, and even follow the person based only on the signal of the phone that his phone is sending, is transmitting towards the UAV base station. This can be extended, this concept, even to multiple users that are spread on the area, and these users can also be connected. There can be also drones that are actually deployed for an emergency situation, and in which the bigger drone that you have seen represents the base station and the mothership of these four. So in this example here, we have the 4 user equipment on the ground. You see these 4 square here, and specifically the user 2 is the one that is active in a bigger transfer of data towards the cellular system. So what you have seen is that the drone, as soon as it got in, detecting the higher data rate requested for these users, moved towards these users in order to cover his needs as well as possible, reducing the distance and so improving potential capacity and bandwidth and so on. When this data flow is not needed anymore, then the drone automatically repositions itself in the middle of the area that is potentially the barycenter of the area that represents the best place to be in case there are no specific communication flow active. Another example of using a robot to improve communication is if we want to explore areas that are challenged for the communication point of view. So in this case, we are imagining it to be in a cave. Actually, this is open. You see the sun coming from the top, but the results are still good, are still valid. So this little drone went to discover this area that has not been mapped before. We don't have any information on, and sends a video back to the operator. These little drones are equipped with very small camera of 240 by 320 pixels, so 320 by 240, and only black and white, and so on. So it's very challenging, but you see that more or less the operator can understand what's happening. And the thing is that when it gets too far from the operator that is placed in the place where they have taken off at the beginning, there is no more connection, or the quality of the video will degrade. So the second drones move towards the first in order to create a chain of relay and allow the first to keep going on in the exploration. This, of course, happens with the third drone and so on. And you see that the first, waiting for the second to act as a relay, can move ahead and go ahead discovering this area and keep sending good quality video to the user. This is the same example, but done into the lab, but just to show that this triggering of taking off and going to offer a relay service is piloted by the RSSI of the signal that is perceived at the base station, that in this case is the computer on the desk, from the device that left and went in exploration. That's when this RSSI is too low, what happens is that the second drone goes and tries to improve the quality of the transmission, now the communication. Now we have done it with the RSSI, but you can imagine several parameters of physical layer or even transport or application layer that might be considered in order to do this equalization of the distance and allow the flow to continue working. So now, to conclude this part related to what robotics can do for communication, there are still a lot of challenges open, especially in this area. These are more research-oriented rather than standard and regulation-oriented, and is how to use how to put together communication and robotic. I told you that the dream somehow was how to include mobility as a communication primitive. So, or the opposite, how to have communication as a control primitive. So, put these two things together in a new protocol stack is something that would be really interesting. How to create communication that are robust and reliable, how to allow ultra low latency communication for robots, for example, industrial robots, how to cope with the different environment, and how to cope also with different rules that are in different countries. This will bring to other declination of the classic Internet of Things, like in Internet of Robotic Things or Internet of Autonomous Things. To conclude completely my talk, just putting all together, the idea of the talk and the main message is that robotics and communication that are considered as separate disciplines and very far from each other with different assumptions and so on, actually, in order happening in the years starting in 2005 when I was a professor at this laboratory. It was something very futuristic, and now it's something that actually you have seen in the videos we are doing. We are putting them together and we are making it work together. How to use mobility to become a control primitive for communication is the main objective and the final objective, but this means to create new communication models that, because the ISO-OSI can actually not represent well and accommodate the robot capabilities inside, the intelligence and the other capabilities that a robot might have. This means also to create new architectures that include the communication within command and control for the robots. One thing that is potentially happening already is that non-terrestrial network, as we have seen with the standardization, for example, pushes towards creating this interoperability and so pushing the standardization part, which is something that is actually still missing. So this concludes my talk. I hope I was not too long. And
thank you, Enrico. Excellent. Really appreciate it. And I asked the audience to put your questions in the Q&A section.
okay.
As you have some questions.
Okay.
In the meantime, I start asking you, you have been on both sides, meaning conducting academic research, also practical research. Especially when you do practical research compared to your classical academic research, what type of difficulties you had or have, and what do you recommend to young researchers when they move to technology transfer, meaning doing more and more practical research, how they should approach this challenge? The reason I'm asking you is there are many researchers in the academic world, they somehow are afraid of practical research because it's more difficult, it takes more time. And they just do some simulations and their objective is just publish something and move on. So what do you recommend to these younger folks, how they should combat this fear and make this step?
I mean, I can say out of the experience with the guys that worked with me, we were scared too at the beginning when it was not clear completely our mandate and what was the objective of the research center. We knew we had to work in applied research, but we didn't know how much applied and how high the TRL would be of the solution that we have. Of course, it was something that in general was would produce fear in the sense that I used to have a simulation that gives me result in half day or some hours, And now you ask me to do this in reality. How would I cope with it? So I understand completely the fear, because it was the same one that we had starting this exercise. However, I must say that putting the things to work for real, it's probably one of the most satisfying. Of course, it depends on the nature of the researcher. Someone very theoretical and very abstract might find this irrelevant, but for people coming from engineering and from researcher coming from areas of real application of the things, seeing that what you are doing is actually working is something that is much more motivating, I would say, than just writing a paper. And these, I would say, and looking at my guys now, the people that worked with me in these 4 years at TII, increase their level of confidence on things and understanding of reality even more. So it gives them the possibility to really know what's happening and to really see with their eyes that this kind of protocol or this kind of architecture is not the best suited for the exercise we are doing or for the mission we have to do, and we need to switch to something that is actually more effective. But also, it cuts a lot of, I would say, blah blah that is normally done by people that never really tried to put things in practice and see what really works. You understand almost intuitively after a while that that's not the right road, and that you have to find another path to reach to the solution you want, because whatever it's said in 100 papers is probably not really tested in reality, and it can be cut off because it's not really working.
You know, the problem is the system pushes the academics to write more papers and try to get promotions and tenure, whatever. And then you know, it's faster to write theoretical papers. You know, I went through all of that in my career research life. And but plus the opportunities, right? Many countries do not have that support for practical work because it takes, you know, more people, more money, more time. And that's why younger researchers take easy out and try to do these assumptions. And unfortunately, those assumptions are surreal, like, you know, making surreal art. Nobody will care. But then, you know, on the other hand, they say, I don't care that people are using it or not. I'm getting my tenure promotion. I have 150 papers and I have this many citations. But you know, the research, the science is missing the contribution, you know, like kind of, as you said, the satisfaction is much more when you see the work you have done is used outside and people are using that. So you know, this webinar is also, you know, giving advice to younger people, not just teaching you basic research. But going back to the basic research ideas, I don't know, you didn't mention these, you know, AI machine learning techniques, which would be very, very, very important for the autonomous systems, as you know, that, you know, we're trying to create these autonomous systems that they will do self-control and self decisions and all that. And like, you know, along the same lines, federated learning, distributed learning, and all of that. So I assume that they're also very important, right? So your research is also based on those issues too, right? I would like to hear your opinion.
Yeah, completely. I mentioned it only for the sensing part as an area or disciplines that is relevant for communication in a multi-robot system, but is actually valid also for the communication itself, for the behavior of the robots or the multi-robot system, how they would work together, what they will do, and so on. We use massively artificial intelligence in general as users. Recently, we have even tried some new, let's say, research direction related more on LLM. So what we do is to instruct the robot on what to do by using LLM. It means, for example, having a little robot that goes on a plant to detect if there is any disease or any potential bug that will ruin the plant, coming back with the information, pictures or just sensors that, I mean, measurements from sensors that represent the environmental condition and the visual part on the plant, and make LLM understand what's going on and produce an answer that is go and spray this I don't know, pesticide or this kind of fertilizer or something else that actually will help the plant go ahead. So we use massively artificial intelligence. We are moving towards LLM and also VLM for robots. We have some research line related to the manipulation, and I didn't mention because it's more individual robots that in the end the communication part is not that relevant, but still learning from a video how to move the arm in order to perform a certain operation. It's also something that we are doing, and reinforcement learning, federated learning, these are all things that are massively used in our algorithms. I would say for the control, for the perception and vision, massively. For the control part, I would say a good part of it. For the communication, a little less in our examples, because in general, communication is just make it work and allow the system to go ahead. So offer connectivity and move on. But on the research part, we are working on that as well.
Are you guys have this Falcon large language model and also version 2? Are you working on adding your research results to that tool also?
Yeah, we are fine-tuning Falcon version 2 now in order this example that I gave you with the plants is actually something that we are doing on Falcon. So originally, I mean, we started with other commercial product, but as we have this developed inside, and the TAI, I mean, one of the most important results and outcome was exactly this Falcon LLM. We are fine-tuning, I mean, we have already fine-tuned it for agriculture purposes, and we are using it for that. So yeah, thank you for mentioning.
I saw a question, but it's not clear to me. I asked the person, Max Tess, I don't know who that is. He says, Professor, could you kindly give some papers on wireless robots you mentioned towards the end of the presentation? I
I
think know what it means, but you know.
Yeah. I think he means the one of the relay, using robots as a relay of a chain of communication. We have a couple of papers in robotics and also communication conferences. They were in the slide. I don't know if you want me to project again the slide, or I mean, it is just at the bottom of there is a recording, I guess, so it will be easy to get the information from the slide. And also for the autonomous positioning of the UAV base station, we have a couple of papers, and they were mentioned below the slide. I think this is what.
Okay. So I would like to make another comment. Recently, I listened to a keynote speech, which was excellent, by the way, and it was about terrestrial and non-terrestrial integration of these networks, and you know, for 6G. And then one of our colleagues asked, she listened to my talk like 25 years ago. Same things are repeated. So now I recommend to younger people again to look at old literature. So, for example, you mentioned this low orbit, you know, these flying airplanes or balloons. And many young people think that it's a brand new idea. So like 3 or 4 years old, I remember I used to work with Raytheon. We had this work on HALO project, you know, high altitude, low orbit project. And we have a paper in 2000, you know, many of you, our young people were not born even 25 years ago. So we published it in IEEE Communications Magazine in 2000. So I recommend to younger people, look at the old literature and learn from the past. Don't think that everything is brand new. Oh, you know,
It's all rebranded. It's just rebranded with new
Exactly.
terminology, as well as there have been, of course, in the meantime, new findings, technological and scientific, that probably those ideas that were very pioneeristic like 30 years ago are now actually doable and exploitable. So that's what changed. But yeah, totally agree.
Yeah,
Low altitude
actually,
platform, high altitude platform are all.
exactly. I mean, that's the point that our colleagues are trying to make, that with all these new AI and machine learning techniques, how can we make these networks much more intelligent and independent? And I understand that. But then many young people think that, oh, it's brand new. Remember, we had this conference, this guy gave a talk like he invented everything like last year. And, I don't know, maybe they should really study the past more carefully and even learn and not to make the same mistakes. That's my suggestion to the young people.
Yeah.
And there is also one other study, I mean, question by Muthana.
Yeah.
And I don't want to hear this word, but unfortunately, I have to read it. It's cognitive radio. I worked like 10 years about cognitive radio technology. He or she, Mutana, says, can we apply or try to involve cognitive radio technology? Please ask, and then I can add.
Clearly, cognitive radio technology is applicable here. Imagine, for example, the problem we have on having a UAV that are users of a cellular system, and they need to be connected, as well as the users that are on the ground, so people that are in vehicles or just walking. These the two of them have different channel that they are able to connect to, because one might be probably flying in a better position, in a better line of sight in respect of a user that is obscured by a building or by a big truck or by something like that. So the distinction of primary user and secondary users is something that, I mean, would immediately require the application of cognitive radio technologies in order to understand which one to favor in a different situation, as well as sharing the spectrum for different mission, for example, or different segment even of the same mission, aerial and marine. They can all benefit from differentiating the type of condition of the type of channel and the condition the channel is undergoing, and detect what is better to do in a certain moment according to that. So yeah.
You know, my suggestion, recommendation to this person is also to others. Cognitive radio technology was very interesting, and I think we can learn a lot from those research results. How do we do dynamic spectrum sharing?
Yeah.
You know, it's very, very important nowadays, especially for the 5G and 6G systems. So we should not count them out, all the results. However, the way that we had in mind this cognitive radio technology will be somehow rehashed and more focused on dynamic spectrum sharing than just, you know, primary or secondary users. That's my opinion. And one more question from me, and then I will ask Alessia to take over. You know, one of the biggest problems or challenges we had here was to have access to the licensed spectrums. And you do a lot of practical research in Abu Dhabi, maybe you do not have that problem, right? So how do you overcome that access to the licensed spectrums to do your experiments? Do you have an agreement or something that maybe
Clearly, we have the possibility. We work very closely with the TDRA, that is the telecommunication regulation authority of the country. As we are a public funded research institute, we have access easily to these people that are also working for the government in the end. And we have been so what we do normally is to inform them of the need to transmit on a certain frequency, and they allow us in certain times during the day and certain areas in the country to do the test of communication that we need to do. It's something that we actually just fill in a form, and we receive the authorization in a few hours. So it's practical and easy, I would say.
That's the adventure of being in a small country, right?
Yeah, yeah.
And you can do anything you want. So
Kind
I
of,
thank you, Enrico. It's always a pleasure
Thank you,
to
brother.
spend time with you.
Thank you.
Fantastic. And I hope that you will be a good role model for many researchers to
Thank you.
combine the theory and also the practical world.
Yeah.
And I observed that 10 years ago when I visited you in Compiègne,
Mhm.
and you were moving more and more practical research. And I was thinking, oh my God, he has the courage to do that. And now you fully utilize that. And I congratulate you for that.
Yeah.
Thank you again for this excellent talk and also your
Thank you, bro.
experience to share with us. Alessia, please.
Thank you. Thanks a lot, Ian, for moderating this session. And thank you, Professor Natalizio, for your presentation. Now we move to the Wisdom Corner, which is based upon the idea to give a unique special angle to this series of webinars, adding a personal touch. So I will start with my first question to you. I would like to ask you, which is your hard-earned life lesson or failure that you would like to share with us that might help somebody attending the webinar?
Yeah, I mean, that's, I have a very, very big one and then many smaller one, I would say. The very big one, actually, I was involved during my years after I was in US with Professor Akilditz. He was interested in keeping me there and try to work together, but for some reason I preferred my own country and going back. But this I knew that it was a very challenging and difficult path, because I mean the situation, especially in those years of university and university system and public research and so on, was first of all the only possibility for a researcher to go ahead in his career. There were very few research centers that a private one that would hire a researcher, and I mean the quality of the research was limited, I would say. So the idea was to have a research career inside the public organism. This was not possible, and I was involved in all the protests at the time against the government that was at the time 2008 2010, and that in the end won the political battle of reforming the system towards a new one that I'm not sure it brought the results they wanted and the outcomes they wanted, but that basically cut off a big part of the, at the time, temporary researchers that had the contract of 1 year and renewed all the time. So I became even kind of a national spokesman for the movement of protest. And in the end, we lost. That was a big failure. And this produced my move to France, where instead I found an environment much more comfortable for a researcher and with many more opportunities than at the time Italy was offering. So I would say it was tough. There were years where being away and having, I don't know, the new country with the language I had never studied, and the situation was really, really more difficult than at home, clearly. But it's something that I guess many people have experienced in their life. For me, I would say even the fact of having lost the political battle was something that was heavy on me, because in the end we were trying to do that for the wellness and the perspective of a country, not only for ourselves. And so I think it was hard. But then, of course, for me personally, this was a big achievement, and it's paved the way afterwards to become a full professor very quickly, and then have the possibility to join TIA in the UAE. And let's say it was the right move at the right time, even though it was a big failure in the sense of losing the battle that we were fighting for.
Thank you for sharing these big lessons, actually, that you have learned. My second question would be, what advice would you give to young people interested in pursuing a career in academia or research? which
Mhm.
skills and qualities you believe are essential for success in academia, in research.
Okay. Yeah, I mean, on this, I have the big example of Professor Akilditz and his own protocol for success that I keep saying and I keep repeating to the people that talk to me, that is this famous HIP-T protocol that is hardworking, integrity, perseverance, and talent. These are the main ingredients, I would say, but on a personal level and thinking of my experience, one thing that I actually learned and that was really relevant for me, that I'm not probably able to apply in all the things in my life, but for work it always worked, was the moment you feel uncomfortable in a work environment, don't stay. Just if you feel your capabilities, your talent, your hard work wasted somehow, just don't stay. Find the next step. Find something that might even be less rewarding at the beginning, but look for your path. Is not you are not supposed to stay in a place that doesn't value you, and
Yeah,
you need to
very
move
clear.
ahead and find something that corresponds better to what you are.
Yeah, wonderful. Fully agree on that.
Mm.
I would like to ask you what initially sparked your interest in your field of study and how did you pursue it really at the very beginning of your career?
Yeah, for this, I was not. I don't know. I always loved studying. That's true. And I remember when I got my master and then I got enrolled in a PhD that my mom, who is someone very modern and very, I mean, knowledgeable, was telling me, but you graduated already. Why are you still going to university? The idea of research in Italy is kind of not so easy. Maybe now it's different, but 25 years ago when I graduated, 20 years ago, it was more difficult in general. So I think first of all was the pleasure of studying, but my idea was to move abroad for some years to go back to my country and bring back some expertise and some knowledge that will be useful to reduce the gap that at the time that part of Italy especially was suffering. However, for marginal problems, at the time the military service was still compulsory in Italy. I was enrolled before my PhD I got a grant from an inter-universitary consortium that allowed me to serve my country by doing research. And so I discovered the life of a researcher. And I think that the biggest thing that attracted me in this sense was the freedom to think of the problem you want to solve, the freedom of defining the time when you want to work and when it's time to stop and so on. And it's not that researchers work less. I think they work even more than people that are, I don't know, in consultancy or in other environments. But it's just because they are motivated by their passion and not because someone tells them to. So I think this the lifestyle of a researcher, and I mean, I felt easily getting in blending in, and the lifestyle is something that attracted me at the beginning and was very interesting. So I mean, I started doing a PhD after this university inter-universitary grant that I got for 1 year. And I had the possibility to go and teach to students, to go to international conferences, and I mean, both experiences were really rewarding for me. Seeing the sparkle in the eyes of the students when they get something that you are transmitting to them, or I mean, having the possibility to deal with people from different countries with different experiences and so on was something that I really enjoyed, and I think that that was the main direction on I would say on my personal choice. Then professionally, what to do specifically, I mean, it came from the fact that at the time telecommunication was something that was pushing. Internet was at the first years that was something spread, and the cellular system were taking more and more space, and it was very interesting. But I will say that, and this is something I must how to say acknowledge that came when I went to US. and I was in Professor Akildit's lab, having the idea of my research. These terms, my research, is something that I learned from the guys that were working with Professor Akildit's. I mean, to me, I was just solving problems and putting them in a paper, and that's it. But having my research, that means something that I really push for, I really contribute on, I really want people to believe me that that idea works. It was something I was not used to, and it was in fact the time that I started working on mobility as a control primitive of a communication system and so on, and that still brings me where I am now.
Wonderful, thank you. My very last question to you. Could you tell us one of the most tangible contributions that you have made in your career that had a direct impact on your life, personal, professional, that you're most proud of? Maybe also an impact on others' life?
Yeah, I think, I mean, even on this, probably there are several that I would think of, but I must say that probably at the time I was still a student, I was involved in an association of students of electrical engineering and computer engineering in Europe. So there are different local committees all over Europe, and they offer the possibility, they organize events, and each of these local committee, and then the one you belong to send a representative of the local committee to see them. This was something very new in the university where I was working on I was studying in. And after a couple of years in this association, I became vice president, European vice president of this association. And I must say that all the people I worked with in that environment, that at the beginning were strongly limited by fears, by thinking we are not enough to meet these people from all over Europe, or I don't know, to deal with people from very different environment, and somehow having this inferiority complex was something that through the work that we have done in this association, we switched the mind of many and showed them that actually you just need to go and experience the thing and deal with the thing that happens, and there is no one superior in the end.
Wonderful. Thank you so much. I really enjoyed this Wisdom Corner. Thank you. Ian, thanks for coming back with us. We are closing our webinar. I'm sure you want to say a few last words.
Yes, again, thanks a lot, Enrico. It was always great fun to be spending time with you and listening to everything you're saying. And I would like to repeat what Maria, one of our Marias, put here in the webinar chat. We hope you enjoyed all our webinar series the last 2 and 3 years of our journal. And please visit our webinar webpage to discover the full program and all recordings of the series. And also for more info on our journal, please visit our website to learn more about our publications and call for papers and how to contribute. We look forward to receiving your papers, also your ideas for the special issues. And this was the last webinar of the season, and we'll take off for 6 months. Alessia is leaving for us for some short time, but she will come back January 2025, and we will continue with our new webinar series. We will have, again, excellent set of speakers next spring. So we look forward to meeting you again. And I wish you all, also Enrico, an excellent summer, and stay safe and healthy. And we'll get back together again. Thank you.
Thank you so much. Thank you, Enrico. Thank you, Ian.
Thank you.
Bye-bye.
Thank you,
Thank you, everybody. Bye. Bye-bye.